When we first introduced the chemical reactions and chemical equilibrium when going from reactants to products, we insisted on the fact that the equilibrium is a dynamic property. That means that there's constantly reactants becoming products and products becoming reactants, even though the concentration of both remain constant. So the next question is, what happens when we disturb a given equilibrium? What happens when we remove some products or when we add some reactants? What happens to the new situation of equilibrium? A very similar situation happens in nature. For example, you may be familiar with the equilibrium between prey and predator. Uh, you may also be familiar what happens to the population of deer in the Midwest when we have removed all those predators. There's a new situation of equilibrium being reached, and sometimes the consequences of that new situation are bad for the environment, for example. This just speaks about the fact that it's a dynamic equilibrium, that there is a constant back and forth between reactants and products. Let me give you an example of that. When you go to higher altitude, unless you're used to it, you will feel a lack of breath. That's because the partial pressure of oxygen is lacking. So that will translate when you have not enough oxygen to breathe, you'll have less oxygen in water, in your blood, which is mostly water. That means that the equilibrium will be shifted towards reactants. Notice that hemoglobin captures oxygen to transport it to the cells. So what is actually painful is the lack of hemoglobin with oxygen that can give oxygen to the cells. So you have reached, in this case, a new situation of equilibrium. The disturbance was removing oxygen when you go to higher altitudes. The new equilibrium has shifted the reaction towards more reactants. How does the body can counteract this effect? If you stay for a little while, several weeks in higher altitudes, your body will create more hemoglobin. It will again disturb the equilibrium so that when adding more reactants, it will provoke a new situation of equilibrium in which now the reaction is shifted to the right. So finally you can have more hemoglobin with oxygen that can be transported to cells and therefore breathe. So this principle is called the Le Chatelier principle. And the Le Chatelier principle just says that when you perturb an equilibrium, the reaction will react towards removing that perturbation. So let me just read it here. When a chemical system at equilibrium is subjected to a stress or perturbation, the system will return to equilibrium by shifting to reduce the stress. Okay, so for example, if the concentration of one component increases, the reaction will reach a new equilibrium, trying to compensate that increase of equilibrium, that increase of that component. So if the concentration of one component decreases, the system will react to produce some of it. So in other words, if you have an equilibrium between reactants and products, if you perturb the equilibrium by removing reactants, the equilibrium will be shifted to the left so that the reaction produces more reactants. And if you remove some products, the new equilibrium will react towards producing more products. So trying to counteract whatever the perturbation does. There's of course a dynamic and atomic explanation for that, and it's because of this constant back and forth. The moment you remove some of the reactants, it means that there is less reactants to become products, so what you end up seeing is that there is a net shift from products to reactants. A very silly metaphor that I use sometimes is that imagine you have 100 players of tennis. You have here's a player of tennis, okay, 100 of them, okay, and have 100 on both sides, and this is the net. So, and they pass back and forth balls, okay. If you remove some players from the left, you're gonna see a net move of balls from right to left. So think of that as the same factor here. If you remove some reactants, it means that there will be less reactants becoming products, so you will see some reactants being created. Alright, so let's see if we can apply this on a specific problem. You have here a balanced reaction, and they're all in gas phase, but notice that this one is solid, and I must remind you that reactants or products in solid phase are not do not appear explicitly in the equilibrium constant. Okay, so situation A, what happens to water if we add oxygen? Well, if we add oxygen, it means we are adding reactants. It will try to consume that oxygen, so the reaction will move to the right, and therefore the concentration of water, because water is a product, will increase. Now, what happens to hydrogen sulfide if we add oxygen? If we add oxygen, it means that the new equilibrium will be reached by moving to the right. The reaction will move to the right. Therefore, if it's moving to the right, it will be consuming the H2S that we have not touched. So the concentration will decrease. What happens to oxygen if we remove hydrogen sulfide? If we remove hydrogen sulfide, the new equilibrium will react towards creating some of that H2S. That means the reaction will move to the left. If it moves to the left, it means it will create more oxygen. And finally, what will happen to hydrogen sulfide if sulfur is added? Well, it depends how it's added, but typically if it's a solid, imagine that it's just a chunk of solid, it does not matter because the equilibrium constant does not explicitly have solids in its expression, therefore nothing will happen. Okay, that should make some sense because the whole idea of this equilibrium is to keep equilibrium constant. So if sulfur does not show up in the equilibrium constant, by adding sulfur or removing sulfur, nothing has changed, and the reaction is already in equilibrium.